Okay, Aida, we are all set for the tutorial session. You are muted. You are muted.
I thought that my tutorial is tomorrow.
Yes, that's true.
Yeah. Okay. Probably then
It's lecture 2.
it's lecture. Okay, lecture 2. Okay.
It's gonna be still interactive. I'm gonna ask questions.
Yeah. Please,
The
lecture
same.
2. Lecture 2. Okay.
Yeah. Okay. So, okay. Okay. So where are we? Where are we? Okay. Yeah. So where we left it with the definition of this map. So I hope some of you had the chance to try it out, the map that for this example. So if you did, we can check it together right now. I'm just gonna write down here how, so it should be something like X, I, J, K, L, because there are 4 now indices, 4 vertices. This should map to something like Y, I, J, K times some Z, J, L times some W, K, L. Did you get something similar? Uh, so yeah. Okay. So now, so I gave you the map and I said,
Aida, can you show the simplicial complex once again?
yes, yeah. Maybe I can just copy here. Yeah, so it's this one here.
Yeah. Yeah. Okay. Okay. Perfect.
Okay, where are we?
Facets. Our facets are relevant.
I don't know how to push this. Okay. It's gonna take more space than I want. Okay. So basically, yes. So I comes from here. J, K, L.
Then there is a change.
Okay. Okay, so we defined the map, and in fact, the kernel of that map, which is now a toric ideal, the map was monomial, and so that one is called that kernel. We will refer to it as I. Where are we? Wait. Oh. We will refer to it as like I delta R is the ideal of the hierarchical model we say with simplicial complex delta and vector R. I'll say a little bit more what that hierarchical model means, but before I do that, so in fact, all the examples we have done till now I claim are types of hierarchical models. So if we take this like the simplicial complex to be the triangle, like the 3-cycle, like the not filled in triangle, then I claim that when you write down the map, you will get exactly the map we wrote down for the not three-way interaction model. And when we talked about the 2x2 minors, I claim that also comes from some hierarchical model, and you can tell me what delta and R are in that case. Okay, so now what is a hierarchical model? So what's the kind of the idea of hierarchical, why the name hierarchical model? So why? So basically is that vertices of delta represent discrete random variables. Okay, so, and the number, so the positive integer Ri for vertex I represent the number of states or options for that are random variable and the structure of delta represent the dependency relations among random variables. So for example, in the case that in this example that I mentioned earlier, so we had here R1 equal to 2, R2 equal to 3, R3 equal to 2. So we have 3 random variables, each of them, so with like so random variable, the first one has 2 number of states, means like it has binary choices. Let's say yes, no. The other one has 3. Let's say we are considering 3 colors, and one can come up with examples that like where these numbers are the number of options for that random variable. And the structure is telling us here that, where are we? Yeah, so the structure, so the missing, this missing edge here is telling us that the corresponding random variables are independent given the rest. So this is telling us that random variable 1 and random variable 3 are independent given random variable 2. So that's kind of the story where this comes from. And one can go back and interpret like this, like why it's called no three-way interaction is because like it's assumed that there are no assumptions, like any two random variables have an edge between them. So but it's not a field-in triangle, so we are not assuming that there is a three-way interaction among all of them. There are two-way interactions, but not a three-way interactions. And if you kind of were to draw delta here, you will get that this, in fact, is the independence model for two random variables. Kind of I gave the answer to B. Okay, so with this, where do we go? Yes, so with this we are in, okay, so, oh yeah, so now we have an ideal. So the point is we have this ideal and we can, so going back, we have this I delta R. So if we fix just to fix delta, and we denote for simplicity I delta R with just with IR, because delta is always fixed. Okay, and now, so remember where this lived? This lived in this R of R, and then we can apply a group action there. So apply S R1 times and so on times S RM. to this R of R, such that similarly to as before, sigma 1, sigma m acts on x I1 Im by acting on the indices. So x, we have sigma 1 I1 and so on, sigma m Im. Okay, and okay, then the claim is that that this IR is this product of SRIs, I from 1 to m, invariant. Okay. Moreover, in fact, this phi of R delta is product of SRIs invariant. And this is kind of the key idea on how one shows that. So basically we have our ideal that we defined. If we act by this action, we still land in the ideal. And why do we do that? This is one of the main motivations of kind of this theory is that, so when working with hierarchical models with where the number of states is very large, these ideals end up to being extremely, extremely large. And in fact, if we increase like just these numbers here in this example just by 1, the number of generators increases exponentially, and they are very computationally challenging, especially when we have these cycle structures showing up. And using these symmetric groups is an alternative way to like reduce the complexity of these problems and to get hands-on on these generators. So, okay, so where are we? Yes. So now I said this is invariant. Now let's look at case 1. So I'm going to give 3 main results on these hierarchical models. So for the first one, we are already ready. So for this one, let's do this setting. So fix. Yeah, so fix. So we have already delta fixed. So fix delta. Okay. And now take or specify vertex I in M. Okay, M was where the ground set of delta. Okay, for each Ri equal to n, so I is fixed. Okay, so we take for each Ri equal to n, consider the ideal I of n of the hierarchical model m of delta R sorry, I'm gonna call this, I don't know how to call it, so do I have space here? Let me write it like this, M, which is delta, and now the vector is R1, Ri minus 1, and Ri plus 1, Rm. So we are fixing every index, every like element in that vector of states except the Ri. The Ri is the one that is moving. Yeah, for example, if we go back to our picture here, let's say this is R1, this is R3, and R2, we let it to be N. So we have the ideal IN for each N. Well, these two are fixed. And now, so the ideal I of N lives, it's embedded, let's say, it's embedded in this ring R of X, C times N. Oh, sorry. Where C is the product of RI's, RJ's, J different from I. And then we take I to be kind of the limit of when N goes to infinity of IN. And so then this one is embedded in this R of X, C times N. Okay, so kind of to make it more obvious for our example, so take R1 equal to R3 equal to 2. And then we have that the ideal I can be, yeah, so this one lives in this R of X 2 by N by 2. But we can also think of this as like, this is isomorphic to R of X 4 by N. Okay, so we just kind of, we do this IK, or let me say like this. Yeah, so basically the kind of the idea is that 2 times 2, this Cartesian product is isomorphic, is in bijection with 4. And now why is this useful? This is useful because now we can think of our ideal I as living here. And since it lives here, we already said that every seam invariant ideal here is finitely, it has finitely many orbits, okay? So the corollary of one is that, so let's, any, how do I state it? Let me see how I wrote it here. Oh yes, let me write this. So for any simplicial complex delta and vector R, the chain of ideals IN and in N, were obtained by fixing all but one Ri stabilizes. So that is the ideal I is finite up to just 1 S infinity. Because we had only one in this case when we let only one vary. Okay, so we go now to, what did I call this one? Okay, so result 1. Now we go to result 2. So for this one, we need some definitions of the special simplicial complexes. Okay, so
Either can you please write that chain so that
okay.
for the above example.
So the chain, which one? Sorry. Oh, here, the chain of ideas. So let me, okay, I can visualize it. So for instance, as an example here, again with that example, this one. So let's say here I had 2, 2, and n. So basically we have the In will be the ideal obtained by the 2 and 2. And so in this case, let's say it like this. So when n is equal to 1, I1 is generated by just x 1, 1, 1, x 2, 1, 1, minus x 1, 1, 2, x 2, 1, 2. And I2 is like x1, 1, 1, x2, 1, 1, minus x1, 1, 2, x2, 1, 2, and then it adds x1 to 1, x2 to 1, minus x1 to 2, x2 to 2. Oh, yeah. And so on. It continues like this in this case. So we have the chain is this one.
I didn't understand the line by fixing one of the index in this particular chain.
So we are fixing these R1 and R3 to be 2. Or they can be fixed other numbers. It does not matter as long as they are being fixed. And the only Ri that we are letting vary in this case is Ri R2. And it's becoming is N. But so this is just going to be the same things here. And then it's x1 and 1, x2 and 1, minus x1 and 2. Can you repeat the question? So
the question is, I was just trying to understand which one is fixed. You say
fixed R1. So here, these are the ones fixed. And this is R2 is not fixed. So we choose the vertex I equal to here. And R2 is N. And R1 and R3, in this case, are equal to 2, but the thing is that they are fixed in this chain. Chain means we have only one thing growing, just one direction, and that is coming from R2, letting to vary, and everything else is the same. So if we were to vary also R1 and R3, the only problem would be that we would not be in a polynomial ring that looks this way. Like that has only one n in the indices.
Okay, I understand. So fixing mean that we are not changing the range for R1 and R3.
Yes.
But
yes.
yeah, okay. I was thinking other way. At fixing these indices are fixed.
So no, fixing the range. Yes.
Yeah. Okay.
Yes, we are fixing. Yeah, thank you. And so in this case, maybe this was a definitely useful discussion because it looks like it was needed. And also, yeah, so we see here in this example, yeah, we are fixing the range of like R1 and R3 to be 2, and we kind of see it clearly that I1 is included in I2 and so on is included in IN. The funny part in this case is that the indices, if you notice, the change is only in the second index. Oh, this is too much. The change is only in the second index. And one can even, in this case, make a guess on and so on. And we go to I here. A guess on I. So I is in fact S infinity of just being applied in the second index. Of just x111, x211 minus x112, x212. Okay. Is everything good?
Yeah.
Okay.
Maybe any question from the audience or confusion? Seemingly everything is okay.
Okay. Result 2. So for this, we need the definition of decomposable. Okay. Excellent. Okay, so a simple complex delta is, we call it reducible if either it is if delta is a simplex. So it's like one of these point line in a triangle or a high dimensional triangle. Or there exists a proper decomposition delta 1 as delta 2 of delta such that what does it mean? Of delta. So in other words, delta is the union of delta 1 union delta 2 and delta 1 delta 2 not empty both, and delta 1 intersect delta 2 is this 2 to the s. We call it, it's like it's a simplex. So for instance, I'm gonna just yeah, so for instance, the example that we mentioned earlier, this one, this is reducible because we have this and we have this. This is delta 1, delta 2, and the intersection here, this is S. But other examples are there, they can be more complicated example of reducible. So for instance, the picture that I mentioned earlier, this one is also reducible because it can be reduced in two parts again, this one and this one. So even though the second part here, yeah, it's not, cannot be reduced anymore. So yeah, so, but
That is a bad example, the second one.
No, these are all reducible because the second one can be written as this one and this one can be reduced in these two. And yeah, so this is delta 1, this is delta 2. And the intersection is a line, so it's acceptable. So delta 1, delta 2, their union makes delta. They are both non-empty, and the intersection is a line, so it's all good. But then if I go with this delta 2, this one is not reducible because there is no way to write this as a union of two other simplicial complexes whose intersection is like a simplex. Okay, so reducible means that you can just kind of do one step. But now if you are able to do many steps till you end up with simplices, then you have the definition of decomposable. Okay, so that's we go to, yeah. Okay, so we have.
Excuse me.
Mm-hmm.
Why the third one is not reducible? You can take two segment on the bow and the third one segment on the yeah.
So you are saying the third one may be reducible?
Yes, I guess. I think
How?
so.
How?
Either label the vertices first. 1, 2, 3, maybe.
Yeah,
The
okay.
third
1,
example.
2, 3.
Okay, take
What
1,
is
2,
delta
and
1?
The intersection is not clear. Not a simplex. Yeah.
it's a simplex. 1, 2, and 2, 3.
And delta 2, you're saying is 2, 3?
No.
Delta 1 is 1, 2, and 2, 3. He says the V. 1,
Oh,
2.
so delta 1 is 1, 2, and 2, 3. So you take this, you're saying you take this as delta 1?
Yeah.
And this,
Okay.
the last one
What is-
for delta 2.
But the intersection, what is the intersection of those? So if you
Got it. Thank you.
yeah. So the intersection of them, yeah, so that's a good example. So the intersection will be this point and this point. So it's a disjoint union of 2 points. And that's not good. It should be like a simplex. So it should contain also the line in the middle, the segment.
Yeah. Thank you.
Okay. So simplicial complex delta is decomposable if either it is a simplex, if delta is already a simplex, or there exists a proper decomposition so like delta 1 as before as delta 2, but now we're with delta 1 and delta 2 both decomposable. In other words, so we did the decomposition and we take delta 1, we can decompose it again, either delta 1 is a simplex, or we can decompose it again and again and again till we end up with pieces of simplices, and the same for delta 2. So for instance, that tells us that the first example.
Excuse me, Aida, whether a simplex is always decomposable or not.
The
If we
simplex
take a
is always
simplex.
decomposable by a definition. So yes. So a simplicial complex is decomposable even if it is a simplex. So by definition, simplices are decomposable.
Simplices
Or,
are decomposable.
yeah, yes. So the first example here Yeah. So this one is also decomposable because like the two pieces, delta 1 and delta 2 are simplices. This one is not decomposable because delta 2 is not decomposable. And the third one is, yeah, if you are not reducible, you are immediately also not decomposable. But something more like that may, yeah. So we can, but however, this class is quite large, so we can like create other examples. So let's say this one. And this is like a decomposable and stuff like that. So one can also think about decomposable ones as like created by starting with a simplex and just glue along edges and along like yeah, points, edges, and triangles and so on, other simplices and so on. Like you can have a constructive construction that is by induction. Okay. So once we know this, then we are ready for kind of. Okay, so theorem.
I have one question.
Yes.
Are every flag simplicial complex decomposable?
I would say a flag simplicial complexes. So my understanding is that you have this inclusion. That's what you are thinking.
Yeah, minimal non-faces are generated by the edges.
A minimal
Or the
non-faces.
standardized
Because
ideal
as
is
you said
generated by
that
quadratic.
decomposable means that we are picking these simplicial complexes and joining them by edges, but
Yeah, whose
vertices
standardized
or
ideal is quadratic.
triangles.
So let me. So you said mean flag complexes.
Yes.
Yeah. What the- Okay, so okay, so what are it? I'm trying to say with plugins. I need to make sure I know exactly the definition of a flag complex. That's why I'm scared to. Are flag complexes defined on like they are types of simplicial complexes?
Yes,
Yeah,
they are simplicial complexes.
simplicial complexes whose standardized ideal is quadratic.
I think
Oh.
that is a simplicial complex, which is like a clique
Okay,
complex of some graph.
Yeah, my first answer would be yes. Uh, I would need to make sure that I know exactly the definition, but yeah, my first answer would be yes, just also because all the ideals of these decomposables here are also quadratics.
Okay.
Yeah. Okay, so maybe as a flag. Okay.
Yeah,
so
it's a flag.
One more question, may I ask?
Yeah.
I think the decomposable simplicial complexes are exactly the quasi-forest, right?
So I would say again, I'll ask what you call quasi-forest, but I would say yes, just because every decomposable simplex can be kind of yeah, can be thought as a fat tree in a way when it is connected. Yeah, I would say yes. Yeah. Yeah. Okay.
Why different names?
By what?
Why different names?
I don't, the thing is, yeah, I've not used that name in my literature, like when I have worked, the name you mentioned. I do know that's all, but yeah, like given a simplicial complex, if you like, what's the word? Contract the right way the simplices, you end up with uniquely with a tree. which I'm guessing that's where your
No, quasi-forest means the facet can be arranged in a way that the ice face intersect with the F1 up to Fi minus 1 is a simplex. Okay.
Oh, so you have an ordering, you're saying. Yeah,
Yes.
then yes. I don't know why. Yeah, you have an ordering. That's also how you get the tree here that I was talking about. Yes. I would say, yeah.
I am not sure if they are the same, but I suppose to be so. I suppose that they are the same.
Yeah, so I would recommend this. So the Dobra, that's what I'm gonna also say soon. He talks about like a construction of this tree, which like looks very much on like what you're talking right now. You put an ordering on a simplices and you have that rule that you mentioned. So I think it's 2003. Yeah.
I have one more question. Is this decomposable the same as vertex decomposable?
I know that it is, the answer is no.
No.
There should be examples like Googling them.
Okay.
I don't have one on top of my head.
Okay, thank you, thank you.
But they are very similar, like a lot of like the
Yes,
shell of
there are a lot of
they are like so near to each other, but somehow, yeah, there are examples. Yeah. Okay, so let's let delta be decomposable. Simplest shell complex on vertex M, vertex at M, which is 1 through M. Okay, so let now so yeah, sorry. Yeah, so for each R in this Z greater than 0 of M, for each like vector of states, let I of R be that kernel of phi delta R. Okay, then now it's a I'm gonna use the word the family or filtration because it's not a chain, it's like has more than just one direction. And the filtration IR or R in this Z greater than 0 M is finitely generated up to S infinity. Oh, sorry. Also, for a lot of questions you asked, my understanding is that there are great people from commutative algebra there that you can also discuss after the talk. Okay, so S, yeah, up to S, I wrote them the opposite again. S M infinity. Okay. So the idea is that if we start with a decomposable simplicial complex and we create any filtration of ideals, I'm taking here the most extreme case where all these states, like all these RIs like are varying, then the ideal is finitely generated up to like the SM infinity as I described. Where is it? As I described here. And moreover, something even better. We have that the ideal I, so if I is the limit when all these Ri's go to infinity of I of R, I is the SM infinity of the ideal I of all here 2, 2, 2. So what this is saying is that if you have a decomposable simplicial complex, you just need to compute the ideal where everything, all the states are binary. And then for any other like problem model where with the same simplicial complex, but these states are not binary anymore, are larger, you permute indices. Okay, so it facilitates computations quite a lot. And
Aida, where are you applying this S infinity to all the indices?
so SM, because I said M here, so there are like this is S infinity times S infinity. So each of them is being applied to the corresponding index. So in all the yes.
So nothing,
But
no range is fixed. No range is fixed associated.
So I took the extreme case. If you want to fix some of them, you can, and it still is fine. If it works for the bigger one where everything is it's like going to infinity, then it definitely works for when some of these RIs are fixed.
Okay. 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 Understand. Thank you.
Okay, and if you like, I'm assuming from the question from the interactions that you all seem to love, like commutative algebra and polynomials. So in this case, I is generated by degree by 2 square free binomials. It has all those nice properties that come with degree 2 square free binomial. Okay, and where are we? Yes, so. And honestly, if you have the structure, I don't want to go into like how I'll give the reference, but I don't want to go into like how you explicitly compute these generators. But it's if you have the simplicial complex, you can like deduce the generators just by looking at the simplicial complex. It can be having like writing things down. That's why I'm choosing to give the reference, but it's like the problem is when you have a decomposable, then everything works perfectly and there's a beautiful panorama. Okay, so now we go to the third part. So now we go to the independent set theorem. And I did not, did I? Oh yeah, I did say this. So Dobra is here and there is some work on from Austin and Sullivan. 002. They talk about the reducible case, but okay. And the result 3 is okay. So you kind of you got the idea that we are allowed sometimes to fix some of the entries, and while the rest varies, and there are instances like in the first instance when we could like let only one vary, then we get finiteness. But if we let more than one thing vary, like the no three-way interaction model told us that, okay, maybe that's not good. So kind of we want to have like hands-on on like what can, given a simplicial complex that is not decomposable, what of these RIs can we let vary such that we have finiteness up to symmetry. Okay, and for this we need another definition. So it's here. So yeah, sorry. So let T be a subset of M. Okay. Okay. So if T intersect F is of size less or equal to 1 for any F in the facet of delta, then T we say is an independent set of delta. So for example, I'm gonna take the picture I started with. This one. 1, 2, 3, 4. So it's very kind of obvious. So if T has just size 1, like result, then T is independent for any delta. And because the intersection with any facet will be less or equal to 1. Now, in this case, can anyone make a kind of suggestion? What are some T sets T, subsets of 1 through 4, that are independent for this delta?
1, 3.
1, 3, yeah.
Very good. So yes, so if we take T, 1, 3 is also works well. But if I take T, let's say, what can I take? If I take T to be, any other thing, this does not work. So if I take 1, 2, then this does not work because T intersect with the facet 1, 2, 1, 2, 3, is size 2. Yeah.
1 to 4.
Well, thank you. 1 to 4. Thank you. Okay. So so the kind of that's the definition of independent. And the claim is that if our set of indices that we let vary is independent, then we do have stabilization, we do have finiteness. Okay, so wherever this is. Okay, so this is fix delta, and let T be the set of i's in M such that Ri goes to infinity, so it's varying. Okay, so if T is independent set in delta, then the family of I and N now is a vector, okay? Or yeah, let's call it N, or N in N to the size of T here. This one stabilizes. Or okay, so equivalently, so that is this ideal I, which is the limit of when all these n i's go to infinity for I in T of I n. This one is finitely generated. It's finite up to, now we call it S infinity to the size of T. Okay, because like the S infinity will act only on the parts that are varying. Okay, so yeah. Okay, any question here?
I can't understand the definition of T. You have a fixed R.
So let me give an
R is
example.
yeah, maybe.
Maybe a good example.
Okay, so an example is let's take something more. I'm gonna take this here. So we have R1, R2, R3, R4. So let's take, in this case, let's take T to be 1, 3. Okay, and this is independent. And let's take, let's say an example is let's take R2 equal to 2 and R4 equal to 3. And so for each R1, R3, consider the ideal I. Maybe I should have, yes, let's call it like this. So for like R1 equal to some R1 here equal to N1, R3 equal to some, let's say N3. We take I of N1 and 3 to be just the ideal with this simplicial complex delta, and with the vector is going to be N1, 2. So what did I do here? 1 second. So I said 2 and 4 are fixed. Yeah. And 3, 3. So this is the ideal. This is I, N1 and 3. So kind of this IN. And here's a vector. And and what I'm saying is now that, yeah, I have I of 1, 1 is included in, let me do it like this. Yeah, I of 1, 1 is included in I of 2, 1 included. I of 1, 2 included in I of 2, 2. So we have this chain. And I'm saying that in order to know what happens, so what this theorem is saying is that in order to know what happens for like, I have here some I of N1 and 2 for N1 and 3, sorry, for N1 and 3 large, I just need to know what happens in a smaller picture. I need to know some, let's say, I have some I N1, 0 and 2, 0, smaller.
Can you show the statement of the theorem above?
So the statement says that as long as these variables that I'm, like these states that I'm letting vary or correspond to an independent set of the delta, then the filtration of ideals that I get stabilizes up to this symmetry group action.
So stabilizes mean that the equality started appearing there?
Stabilizes, yeah, stabilizes means that
The operator of, under the operation of sigma?
yeah, stabilizes, maybe, yeah, I should, okay, so I kind of omitted, I think, as a definition. So definition here. So I'm gonna write the definition for, oh yeah, so we say, so filtration, I'm gonna call it IN, or N in some N to the M, stabilizes up to, let's say, this SM infinity, if there exists some N0 in N to the M such that I of N is equal to S n, where is m? N of I and 0. So it basically is saying that for large n's, we don't have any new generators that do not arrive by applying these permutations.
It means that sim invariant.
Yes, sim invariant is
Both of them are not the
definitely
same.
there in the definition, but we have equality right now.
Yeah. Okay. There is containment, and here it is equality. Okay.
Yes, eventually, so this is the picture in general, the one I'm here, but I said in the definition of a filtration that we can apply to like this, for instance, this one here, we can apply as n times Sn1 times Sn3 to this one, even though n1 and n3 are larger, and we land here. So if we go to
Okay.
um, yeah, so basically it's this one.
This is sim invariant, and if the equality hold, then we
Yeah, so
say that.
maybe yeah, I went with like, oh, stabilization is intuitive, but maybe I was, yeah, I definitely, it looks like I was being ambitious. So if 3 is equality for some like after, yeah, for n or m greater enough, then we have stabilization. But this sentence is equivalent to saying that the ideal, the big ideal, the co-limit is finite up to symmetry. So if we don't like the word stabilization, we can just say that here. If we don't like the word, it's like that's the same as finite up to symmetry, the limiting one. Okay. Is that more clear?
Yeah.
Okay. Okay. Okay, so tomorrow we will work more examples on how exactly how this looks like. So that's, I don't know if I'm choosing not to go deep into examples. But yeah, so where are we now? So okay. So do we have any questions?
Yeah. So far, so good.
Okay. So maybe
we can stop here. Yeah. Do you want to introduce something new?
Oh,
Conclude.
I don't know. Okay, this is the time where I stop. I don't. Oh, yeah, you are right. Okay, then I think then this is a good place to stop.
Okay.
I will share some notes like after this, and I will share some codes that when folks can like input delta in and r and get as output this ideal I delta r and like see how these examples look like.
Aida, thank you very much. The way you are constructing this I delta R,
Uh-huh.
and particularly in the above example, so I think the equality holds from the beginning, just like constructing the sim invariant or ink invariant chain of ideals.
So okay, this equality does not hold in general.
Mhm.
It doesn't. And the example of the no three-way interaction model is like the one example. Like
Mhm.
for that one, so if I take so if I take this one here, and let's say I give this 2 and then I take R1 oh, so let's take R1 equal to N1, R2 equal to N2, and R3, I'm taking it equal to 2. And then I have this chain of ideals, I, N1, and 2. And I claim that this does not stabilize.
Okay. Okay.
And this is because, yeah, so one kind of idea is, I hope so it's because the ideal I, N1, and 2 requires generators of degree minimum of, okay, I'm assuming N1 and then 2 here are greater than or equal to 2. This requires a minimum of 2 times minimum of N1 and 2. Yeah. So when N1 and 2 increase both of them, then the minimum of them also increases. So every time I increase N1 and 2, anytime I need generators of degree 2 more. So that's kind of the main idea on why this does not stabilize. It is invariant. Every generator, so I and 1 let me say it like this. More, let me not use N1 and 2. So I here, for instance, if I take 2, 2, requires generators of degree 4. And this is included in I of, let's say, 3, 3. But this requires generators of degree 6. So I cannot explain generators of degree 6 that show up here by doing symmetry permutations in the generators of degree 4 here.
Okay, okay.
So I do have a filtration, but I do not have a stabilization.
Okay, thank you. Are there any questions from the audience? Right. Yeah, go ahead.
Thank you for this nice lecture. I have two questions. The first one is you mentioned result by Hiller in your first lecture that if we have this polynomial algebra over the C by N capital N matrices, then any symmetric invariant ideal in R has a finite generating set up to S infinity, right?
There exists a finite, yes.
Yeah. So in classical invariant theory, we have a similar result by Hilbert, which says in the finite variable case that if we have a reductive group, then if it admits an action on polynomial ring in finite variables, then we always have that the ring of invariants is finitely generated, right? In particular for Sn as well.
Yes.
So is it a straightforward generalization of that result, or do we need some more hard work?
So the aim of that result is the generalization of what you said on noetherianity in infinite setting up to symmetry.
Yeah.
The proofs the proofs. So this requires this additional factor. Now what your question was, is this more difficult?
I mean, is it a straightforward generalization? Because for
it's
for
not a
reductively groups,
straightforward,
we have the same result.
so it's not straightforward generalization like that. I would definitely not say. There were I think the first proofs were more pages, and then it became more with time, when we understand better, we can write the proof better. And the proofs are done not even in the terms of sim, they are done in terms of another operation, the operation by the monoids, monoid, that I'm not introducing here, because it makes handling better of the problem. So I would you can I would say definitely has more work. I also would give you the references on where to look. I also, you will have the references on where
Thank
to
you very much. And I mean, is there any algorithm to construct these, or I mean, the proof is just theoretical proof?
Yeah, so that's a good point. The proofs are theoretical. Yeah, the proofs are theoretical. Yeah, that's
Okay.
like, and then
Okay.
in cases, the thing is that many times people start with something that is invariant already, and the kind of the finding the generators, usually that's not the big deal, because that's how they start defining the kind of the infinite object. They take a finite set of polynomials and they act on it by symmetry, and they that's how, like, usually that's how the construction. The other way, then it's more work, so if you don't start that way.
Okay,
And then,
sorry. The other question is, I didn't fully digest the definition of decomposable simplex, because we are defining a notion and then we are using the same notion in the definition. So I didn't get it.
yeah, so the point is, this was like a definition by induction. So yes, here. So we have a we have a simplicial complex given to us. We want to know if it is decomposable. First, we're like, oh, is this a simplex? If it is a simplex, then done is decomposable.
Okay.
Let's say this is not a simplex. Okay. Then one asks, okay, can we write this as a can we write this as a union of two other simplicial complexes, um, non-trivial, so none of them is empty, kind of not a silly one, such that the intersection is a simplex. Okay, are we okay with that part?
But that was the definition for reducible simplex.
Yeah. So that's why I'm saying the decomposable is just you reduce again and again and again till you have only simplices. So that was the first part, is like, can I reduce it in two parts, smaller parts? Then we're like, yes, okay, I can do that. Then, I mean, as you said, reducible. But then I go to smaller parts and I ask the question again. Are these simplices? If they are, yay, done. If they are not, can I reduce them again? And when I reduce them, are they simplices? If they are not, can I reduce them again and again? And so you ask this question until, if you ask this question and at the end you only get like simplices, pieces of simplices, then yes, you had a decomposable to start with.
I understand. Thank you very much.
Otherwise, not.
Yeah, thank you very much.
Thank you. Are there any other questions? Just one comment. Do you know about the definition of multi-complexes?
What is the definition of multi-complexes?
Yeah, this just like simplicial complexes. This is defined on the index set n with singleton, so 1 to n. So multi-complexes are defined on a r to the raised by n. So where
Okay, so the vertices are indexed not by numbers 1 through n, but by tuples?
almost the same way, the way you are doing it, like a tensorial notation.
Yeah, so for instance, you're saying, for instance, I can have like,
so I think the definition of multi-complexes is given
like 1, 1, 1, 2. Like this?
And even the triplet too. Even you can label
Yeah,
them.
but
And then again, the order is defined on for instance, if in this particular case, one can view it. In fact, it is given in the book of Stanley, where instead of relating a simplicial complex to a scale-free monomial ideal, one can relate a multi-complex related to any monomial ideal with even higher power. And when we are taking a monomial from Rn, so regarding to every monomial, there is a corresponding vector in Nn. And the structure is kind of one-to-one correspondence. So scale-free monomial ideal correspond to simplicial complex, but a general monomial ideal related to a multi-complex, and the indices is similar to what your structure suggests. It is almost the same. But I was just trying to understand, because there are not many papers known in the case of multi-complexes. So multi-complexes theory is quite an ignored theory in the area of combinatorial commutative algebra. Very few papers on multi-complexes.
So when for instance, when I want to write this one,
Yeah.
I will need
So
to
just draw the XY axis. XY axis.
oh
The plane. Yeah. In this way, just identify where is x1
oh
square.
x1 squared. So where should I put this in 2? Like 2 0? No, what is here? This one?
Yeah, this one x1 square. Yeah.
X1, x2.
And then x1, x2 is there. Now you identify all so it will divide the plane into two parts. One is inside this ideal, all the monomials which are coming. So just draw the staircase, staircase.
Oh, yeah.
Yeah, this one. Yeah. And upward as well. X1, x2, vertical. Yeah.
I removed the
So now you are left with all the monomials which are not the part of this particular region. So all those particular monomials are the k bases of S quotient I, and they form the structure of the multi-complex. And they use the notion of okay. So there appears a Stanley decomposition, and the Stanley decomposition deals with the infinity notation as well, because the y-axis is going from y1 to y infinity.
Yes.
And similarly, x-axis is bounded, so we have only one x left, x1.
Yeah.
So this associated with this particular structure, Herzog and Durin-Popescu has a paper. They define the algebraic structure associated to multi-complexes, and the similar kind of description is given in the book of Stanley and multi-complexes. And the theory of Stanley-Reisner ideal extended for a general capital. But this is a similar kind of story, but I was just curious because multi-complexes are quite an ignored theory. Not Herzog and Doreen Popescu, not Hibi.
I don't remember which one.
And Doreen Popescu. And they're very less, I think, studied algebra of the multi-complexes, but the structure is something like that. Even one can extend the staircase theory to, I'm not sure whether this is discussed by Strumfels and Ezra Miller in the book, but some kind of structure they also had discussed, but I think multi-complexes is kind of befitting theory, which is maybe
Do they have
new
a,
dictionary.
is there any can one construct a graph with this? Can one associate a graph?
Actually all these stories arose around the conjecture of Stanley, which was about Stanley decomposition. People were interested in attacking this problem, which was later on disproved by Clevans et al. So the problem of nice partition, whether partitionable simplicial complexes or something like that. And all those things relate with the structure of multi-complexes. And Herzog and Doreen Popescu has extended the definition of shallability of simplicial complexes for the multi-complexes. And then in the multi-complexes case, there was a kind of a filtration they were using if the associated ideal. And then there is another paper which is by one of the student of Doreen Popescu. He associated another kind of ideals associated to multi-complexes, but those ideals don't seem much more interesting, probably because the ideal give rise to Artinian structure, full dimension 0. So that's why I never been cited. Nobody, that paper got no attention. But that ideal, because people were struggling in order to relate a structure associated to multi-complexes, that is what I perceive. So probably this particular theory fits quite well with the construction of multi-complexes. Probably. Because everything is asymptotic here.
Okay, yeah,
Just a comment.
Yeah, I'm learning here from you. So I
Sorry.
give more. Yeah, no, That's good. Maybe we should add it to the problems. Maybe, yeah.
Yeah, maybe. Yeah.
Yes. No, thank you.
Any question from the IBS side? Okay, if this is the case, we will upload today's lecture recording, and either please share these slides with us so that
Okay.
we can place it on the website, and all the discussion and everything will be there. So definitely, the participants are curiously attending everything, but definitely it is really hard to absorb everything at the spot. But thank you very much, Aida. You make it quite elaborative and keep everyone interested in the
Thank you. Thank you
object.
for the questions. You made it definitely easier. So I have a hope that definitely you heard me.
So, oh, I think this topic is quite close to everyone now, what you are discussing
Oh,
actually.
okay. That's very good to
Thank
hear.
you. Thank you very much. Thank you. We'll see you tomorrow. Thanks, Aida.